Hello, this is Dr. Oz. In this video, I would like to talk about local versus global optimum. And so local optimum is the best solution within the nearest neighborhood versus global optimum is the goal for an optimization model to find the overall best solution. Let's talk about concave and convex functions. A concave function is a function that's like ball shaped down. So it's say shapes like this. And these are some examples of concave functions. So why do I talk about concave functions now? Because these are the type of functions that are easier to find the global optimum. So let's take a look at an example of a concave function, which is y equals to, or fxy equals to minus x squared minus y squared. It's this ball shape, and this kind of models, it is pretty easy to find the maximum point right here, because no matter where you start, let's say if I start here, you just go this way and then you will find the best solution, and then if you keep going down, if you keep going, you will start going down. So that's why no matter where your initial solution is, as long as you just keep moving the same direction, that is the Lagrangian, using Lagrangian multiplier, um, basically you will find this peak point. All right. So this is a concave function. Let's talk about the convex function. Basically, convex functions are the opposites of concave shape. These are ball shape up, and these are some examples here. And here we are trying to find a minimum. And again, same idea, no matter where the initial solution is, as long as I use the derivatives to find the function, the values are improving my objective function the most, which is going down. In this case, this is a minimization problem. I will find the minimum point. So let's talk about an example here. Imagine that I would like to solve this problem, finding the maximum of this function. And as you guys remember, sinus functions are shaped like this. So basically, it can go from negative infinity to positive infinity, and it oscillates. So if you want to find maximum, should I get this one or this one, or which one, this one or this one? So which one is the peak point? So that's why it is important to have a boundary for this kind of problem, because it goes negative infinity to positive infinity. Anyway, so I don't want to, let's say if I start here in this problem, and if I keep improving this problem using derivatives again, I could go this way, and I could reach here, and then when I keep moving, my value will go down, and then my solution from Excel Solver or another software package that you are using will end up this. But this is not a global optimum. This is a local optimum. Global optimum, I know it's here. So that's why this kind of problems can get tricky. All right. So let's go ahead and run the model. Before I do that, though, let me just show you the shape that I would like to show you the trick. For example, this is a complex function, nonlinear function. As you see here, I have a value here, a value here, a peak here, a peak there. So which one is global? So it can get difficult. Or the minimum here, minimum there, minimum there. Which of these ones are local? Which one is the global minimum? So those are the tricks that that we need to consider. All right, so let's create an Excel file using this problem. So let's create our Excel file, and I would like to start with the parameters. I have X values here, and let me zoom in, and I have Y values. Let's say my X and Y values have parameters, upper and lower bounds. So lower bound and the upper bound. So lower bound for X, let's say 0, and upper bound is 1. And Y, again, 0 and 1. And in this function, I have pi, so I will use that. pi. In Excel, you can use the pi function to find the value of a pi. Open parentheses, close parentheses, which is 3.14, and goes on and on. And I have coefficients here for x, and I have coefficient for y, which are in this problem 5 each. All right, so based on these given parameters, now I would like to create a model, optimization model. And this model, I would like to find a maximum value. All right, so the objective is maximize the function. This could be a profit function, for example, for a company. All right, so I would just put it right here, green cell. Second component, decision variables. In this case, I have two decision variables, which are namely x and y. These are my yellow cells, decision variables. So I can now write my objective function in terms of my decision variables, which is given as x times sinus x times sinus function, and then 5 pi x times pi times x, and then y, same thing with y, which is plus y times sinus 5 times pi times phi. All right, and the if I give us a value of 0 and 0, and my value is 0, if I give a value of 1 and 1, my value is this value right here, very close to 0. All right, third component is constraints, subject to. So I have upper bounds and lower bounds for x and y. So maybe I can name x lower, x upper, y lower, and y upper. And constraints again have left hand side versus right hand side values. Okay, so the right hand side value for x lower is 0, x upper is 1, y lower is 0, and y upper is 1. And the relationships greater than or equal to, less than or equal to, greater than or equal to, less than or equal to. And the x value here is here, and x again, y, and y again. All right, these are my constraints. And why is this a nonlinear program? Because my objective is a nonlinear function. All right, so now I need to use solver under data tab. If you don't have solver here, again, file, options, add-ins, analysis toolpack, go, make sure solver is checked, Click OK. It may take a minute or two. And then on the data tab, you will have solver. Then click solver. Let's start with the objective. Objective is this function right here. And it's a maximization problem. And yellow cells are my decision variables. All right, so let me just don't add any constraints now to see what's gonna happen. Again, I'm using nonlinear program. Let's again eliminate even the upper and lower bound for x and y. So I just uncheck this one to see what's gonna happen. If I try to solve this, you can see that solver has converged to the current solution. All constraints are satisfied. Okay, so what does it mean? So looks like Excel found a solution for me, which is 1.8, and the values are 0.9 and 0.9. Okay, so is this the best solution, right? That's the question that we need to answer. So 1.8 is it the best solution? Okay, so to be able to answer this question, I need to try different starting values because I know this is a very nonlinear function, and I want to make sure these values are the this is the highest value I can achieve. All right, so what I'm gonna do is if I use these boundaries and start with, let's say, x0, y0, and if I solve this problem with the constraints, data, solver, let's make sure this is checked, at my left-hand side, I want this value to be greater than or equal to this value, at I want this value to be less than or equal to this value, at I want this value to be greater than or equal to this value, at, and finally I want this value to be less than or equal to this value. Click OK. So if I solve this problem right now, my result is, okay, it says it found the optimal solution, but let's see whether that's the case. Now I know that based on those constraints, I got the best value of 0.23, but as you know, without those constraints, I got a different value, which was 0.9, 0.9, and they were within these boundaries. So obviously this is not the optimal solution. This is a local optimum, but it's not a global optimum, right? So I would like to do a different thing. What if I start from 1 and 0 starting point? But am I gonna get 0.2 or am I gonna get something different? So I will solve the same problem. Again, previously the answer was 0.232. Now I change my starting point and solve the problem again. And now my result is 0.9. Oh, interesting, right? So now I got a different result. Both cases, Excel said that I got the best solution, but obviously this one is better than the previous one. So you, I think, got the idea here, but I want to show one more example. If you start, let's say, from 1 and 1 location and solve the same problem, now you will get even a different solution, which is 0.1. Looks like I got 1.804, which I think that's the best solution. So what is the deal here? So if you try different initial solutions, basically you are getting different final solutions. So if I start with this starting point, correspondingly I will end up with this point, and these are the values. And as you see, this is the global optimum, but these are all local optimums. So that's the problem with with nonlinear programs, because these are all the peak of those hills, but real mountain is this one. To be able to find that real mountain, what I mean by that is real mountain is this one, instead of getting stuck here. So what we can do is we can start with multiple different starting points. Let's say I can start my journey here, 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 here. And the more location you start with, the higher chance that you will find a true peak point of the mountain, right? Global optimum. So how can I do that in Excel? All right. So let's do this. Let's start with 0, 0 point again. But instead of just starting with one single location, what I'm going to do is randomly, I will use multiple starting point. How do you do that? Go to options, and under nonlinear, you will see here, use multi-start. So I want to start in, let's say, 100 different starting points and see which one is the best. If I click OK, again, for complex model, you may not be able to do so many because it will be CPU intensive. But okay, so now I want to make sure that my variables have upper and lower bound, sounds like. Okay, how am I gonna deal with that? I thought I gave already. Let's take a look at it again. Okay. All right. So what if I don't require bonds? And solve it. Okay, so it looks like it is getting stuck again. So obviously there's a problem here. So how can I really handle this problem? One way for this problem to solve is starting with multiple starting points manually, and we found the best solution starting with 1 and ended up with 0.905, 0.905 for y as well to get 1.8 value. All right, so but how can I get this same thing for multi-start, right? So I can do multi-start value and choose the multiple start values, but it looks like I'm getting a warning here. I'm wondering what I need to do quickly. I think I'm probably doing something wrong here. Let's see. All right, so objective function, I want to maximize this. Decision variables are those. Constraints are given. And then I'm gonna click on options, nonlinear, and I would like to use multi-start, 100, random seed 0. Let's say I require bonds. Okay, and now how am I gonna require the bonds? Okay, let's see. So normally when I click on this, bounds required, I provide the bounds here. That's why I'm trying to figure out what is going on. Maybe solver wants bounds in a different way. Okay, so looks like maybe Excel doesn't like the way I solve this. So maybe instead of putting those constraints like this, I will do something different. I'll delete these constraints and I'll provide those bonds directly. Let me just reset all. So let's do objective green cell again. It's a maximization problem. Decision variables are here, and let's add this. I want this value to be less than or equal to 1. I want this value to be greater than or equal to 0. And I want this value to be less than or equal to 1. I want this value to be greater than or equal to 0. Okay, I just did the bounds manually like this. All right. I think now I can use multi-start option, and hopefully it will work this time. Okay. Yes, it works. So it looks like the problem is Excel doesn't like it in this way. Excel wants us to put it this way, which is kind of interesting. Anyway, that's it for today. I just show you to find a global optimum instead of local optimum, you can use multi-start approach in Excel. That's it for this video. Until next video, enjoy business analytics.